Presenting are JP, Jonathan, Jack, James, and Helen, and we're talking about spacecraft attitude sensors.
Spacecraft attitude sensors can output a range of data relevant to determining spacecraft position and orientation, whether that data is relative or absolute.
The sensors we will be discussing fall into two categories, relative and absolute. Relative sensors determine the rate of change of attitude, so they require an initial attitude in order to work. Because of this, they are less accurate than absolute sensors, which find the position of other objects, such as the Earth or stars, to calculate the spacecraft's attitude. For relative sensors, we will be discussing the gyroscope, and for absolute, we will be discussing horizon sensors, Earth sensors, orbital gyrocompasses, sun sensors, star trackers, and magnetometers.
The first and only relative space attitude sensor is the gyroscope. The physics of gyroscopes were derived from spinning tops. John Serson, English sea captain, thought this could be used to create an artificial horizon at sea, diagrammed on the left. Johann Bonenberger picked up the idea and coined the name gyroscope, diagrammed on the right. Before long, the militaristic potential of this invention was realized and it began mass development, leading to its use in ballistic missiles and airplane sites, such as the Sperry bomb sight pictured on the left. Contemporary gyroscopes physically are quite varied. An incredibly accurate gyroscope, pictured on the right, uses a spinning superconductor. At their core, gyroscopes measure relative angles. It's possible to gather this information due to two important gyroscope properties. If no torque is acting on the gyroscope, it always points in the same direction in ECI. With torque, gyroscopes precess in a predictable direction and magnitude. As a result, one can either determine their attitude in an absolute reference frame or apply a known torque to the device to determine their relative angular velocity. Gyroscopes have advanced considerably in the past 200 years. There are several different physical forms of gyroscopes. Despite the many varieties, they all output the same information. There are three primary classes of gyroscope: mechanical, optical, and microelectromechanical. Mechanical gyroscopes come in two different forms, displacement and rate. While the displacement gyroscope determines angular position of a moving object, the rate gyroscope measures object angular velocity. Optical gyroscopes send light around a spinning disk in different directions. The time differential between how long the light should take to complete one revolution and the time it actually takes yields the angular velocity. MEMS gyroscopes specifically use vibrating elements, which allows extreme miniaturization. This is the kind of gyroscope seen in smartphones. It operates on the principle that observed Coriolis acceleration is proportional to angular velocity. Gyroscopes have a variety of applications. Aircraft and spacecraft inertial navigation systems, such as the CMG and the ISS. The superconducting gyroscope on Gravity Probe B measures the warping of space-time around a gravitational body. Gyrocompasses are used in most planetary-bound vehicles to determine true north.
Now I'm going to talk about horizon sensors. Horizon sensors were developed in 1958 for use in the Jupiter rocket reentry experiments and for the Air Force Discoverer program. The sensors developed for the Jupiter rocket evolved into sensors used in the Mercury, Nimbus, Biosatellite, Aero, Vela, and Agena programs. The sensors developed for the Discoverer program evolved into the sensors used on the OGO and Gemini programs. These sensors can be divided into three classes: scanners, edge trackers, and radiance balancers. The figure on the left depicts a conical horizon scanner. This scanner has two sensor heads mounted on the satellite with their axes parallel to a pair of vehicle rotation axes. When the optical element is rotated by a motor, the field of view sweeps out a cone centered about the vehicle axis. The central figure shows an edge tracking sensor. Edge tracking is achieved by driving a detector field of view to a particular location relative to the horizon. The third figure is a radiance balancing sensor. The radiance balancing technique assumes that when a radiance balance is achieved, the sensor optical axis is pointing at the center of the illuminated Earth disk. These sensors are often designed to utilize the thermal discontinuity at the edge of an optically formed Earth image, so they may be thought of as strictly temperature sensors. The Mercury sensor had many issues that have been improved, but not without sacrificing weight. The OGO sensors performed well with the exception of an optical obstruction that caused the orientation of the sensors to be off. The Pegasus was used to define the approximate Earth direction for a tumbling vehicle.
Next, we will be briefly discussing Earth sensors. Earth sensors are a type of horizon sensor, and so their functions are pretty much the exact same. They are used specifically in low Earth orbit by taking measurements of Earth's infrared emissions to find the horizon. They are relatively inexpensive and aren't as accurate as some other measurements.
Now on to our next attitude sensor, the sun sensor. Early sun sensor applications consisted of guidance of ground-based telescopes, heliostats on solar furnaces, and automatic sextants for navigational use. The first use of a sun sensor on a spacecraft consisted on determining the attitude of a spacecraft based on the position of the sun relative to the spacecraft. Since then, sun sensors have been employed on spacecraft and scientific instruments to determine attitude, detect spin rate, and other guidance mechanisms. The sun sensor is relatively similar to a remote sensor, in that the spacecraft must orient itself to where the sensor is able to capture the designated object in its field of view. This will allow the sensor to measure and obtain the data necessary for mission objectives, identify the sun, and use its position in space in order to find its direction with respect to the body frame of the spacecraft. Typically, sun sensors indicate the orientation of the sun with respect to a reference frame by detecting the intensity difference between two sources of radiation arriving from the solid angle determined by the sun's boundaries and that arriving from adjacent regions within the sensor's field of view. There is a variety of different designs and applications, but normally sun sensors are designed to output two different signals, a digital and analog signal. The major performance parameters are accuracy, stability, field of view, transfer function characteristics, resolution, and reliability. Sun sensors have a wide range of applications. A few examples of sun sensor application in modern technology are meteorological systems, tracking systems, navigation systems, and spacecraft attitude determination and control.
Up next, we will be talking about star trackers. Humans have used the stars to navigate for thousands of years, dating back to the ancient Minoans. We have also been using stars to navigate since the beginning of space travel, with early spacecraft making use of sextants, an invention made in 1731. Nowadays, star trackers are the most accurate method of attitude determination, since they use fixed stars in the sky. Modern star trackers work by using 3 cameras to find stars and then comparing them to a database of known stars to determine the spacecraft's attitude. Star trackers work by using pattern recognition to find constellations and then triangulating the spacecraft's position through the use of 3 different cameras. There's 50 to 60 main navigational stars that are used in the star catalog. Star trackers' applications are very narrow in aerospace, with them only being used for spacecraft attitude determination and control. But in other subjects, such as astrophotography, star trackers are used to position the camera so it's viewing certain stars in the sky. Additionally, star tracking apps have been released on smartphones that use similar but less advanced technology to recognize constellations in the sky for people who are stargazing.
Now on to our next attitude sensor, the magnetometer. These have actually been around for a very long time. The first version of the magnetometer is something that I'm sure everyone is familiar with, the compass. Invented in around 200 BC, it uses a bar magnet to show a two-dimensional vector of a magnetic field. These are very useful for guidance on the surface of the Earth, but are not good at telling the magnitude or direction in 3 dimensions of a magnetic field. The first modern magnetometer was designed by Carl Gauss in 1833. In it, he used a bar magnet suspended by a gold string. In his experiments, he was able to measure the Earth's magnetic field by observing the angle of displacement and the period of oscillation of the bar magnet. The angle of displacement allowed him to calculate the direction, and the period of oscillation allowed him to calculate the magnitude. Today's magnetometers can measure the variances in Earth's magnetic field while in orbit. They work by reporting both magnitude and direction to the guidance systems. It is important to note that there are 2 main types of calibration for these magnetometers. The first is an absolute calibration where known material constants are used to find the strength of a magnetic field. The other way is a relative calibration, where the values of a known magnetic field are used. This way, the materials used aren't that important, just the accuracy of the initial magnetic field. Once the data has been recorded, it can then be sent to the onboard computers. Based on the readings, the computer can accurately tell where the spacecraft is over the Earth and the orientation the spacecraft is in. Coupled along with the known magnetic dipole of the spacecraft, or the residual electric field resulting from the electronics on board, the magnetic torque on the spacecraft can be calculated. This will help the spacecraft correct its altitude if needed.
Spacecraft attitude sensors are a necessary technology for a variety of objectives in both scientific and engineering environments. Their performance metrics have verified and provided important data required to evaluate position, velocity, acceleration of spacecraft that we launch into space. These sensors allow us to guide and navigate our spacecraft and study the final frontier.